Hi there, you're welcome back to my channel. In this video, I'll be taking you through another problem in area of region between two curves. Find the area of the region between the graphs of f of x is equal to 3x cubed minus x squared minus 10x and g of x is equal to minus x squared plus 2x. This is application of integration problem. To handle this, you need to graphically represent this so that you can easily do it. Mostly, if you want to find the area between a region, because it's a region, it has boundaries. So boundaries are the values of x which are common to these two curves. That is where they are meeting. So in order to find those boundaries, what do? You equate them. So 3x cubed, right? So we are looking out for what is common between these two. 3x cubed minus x squared, right? Minus 10x should be equal to negative x squared plus 2x. Okay. So to solve this, you simply have 3x cubed, right? The x squared here will obviously cancel this, right? It will just cancel it to 0. Then I'll have my minus 10x here, that'll be minus 12x equal to 0. Okay. So at this point, what do I get? Factorizing 3x out, I'll be getting x squared minus 4 is equal to 0. So I'm going to have x to be 0, x to be what? Minus 2, and x to be what? Positive. So these are my points. So when I come here, 0 is a critical point, minus 2 is a critical point, then 2 is also a critical point. What do we do next? You have this curve here. D of s is equal to negative s squared plus 2x. I don't mean plot this, but you have to represent this here. Now, is this a maximum or a minimum curve? You differentiate these two times. If you get a negative, that is the second derivative test. That means that it's going to be maximum. If you get positive, it's minimum. So when I differentiate it first, I'm going to have what? Minus 2x. On my second derivative, I have minus 2. So meaning my graph will look something like it will going to pass through. But remember, it should pass through all these three, right? It should pass through all these three. So we are having s values minus 2. So it should actually meet our function at the point. It doesn't necessarily mean that it should pass through. Like, I mean, yes, it will have a different way of interacting with this, but the boundary is once I draw some dashes here and once I have my another dashes here, this whole thing shouldn't exceed this. That is the idea. So meaning that I'm going to have something like this, right? So depending on the plotted values, that is how. So I'm going to have something like this. So something increasing, but rather it goes and come. Okay, it goes and come like this. Then let's see for this part. Yes, this is quite a complex one. So if you have this is interacting with 2, negative 2 and 0. Okay, for that reason, from negative 2 to 0, will this curve increase? From 0 to 2, will it increase? How do we know this? Right? How do we know this? Okay, so you have to first your first derivative test is used for finding the increasing and decreasing. So when I differentiate it, I'm going to have what? 9x squared minus 2x minus 10. Meaning that from negative 2 to 0, I can put anything like negative 1. So when I put negative 1 here, what am I getting? I'm getting what? 9 plus 2, which is what? 11 minus 10, which is 1, meaning it to be increasing because it's positive. Your first derivative test is used for increasing and decreasing. Once it's positive, meaning it's increasing. So I'm going to have something here. Yes, so this is my second curve. So this one was the g of x, okay? Then now this is f of x, but f of x will have different regions. So the first part is between negative 2 and 0 because it's s cubed, take note. Then the second part is from 0 to 2. Will it be increasing or decreasing? Let me take something like 1. I'll get 9 minus 2 minus 10. That is 9 minus 12, negative 3, meaning to decrease. So to come like this. So this is the nature. This is coming down, it move up, then it will catch up with this curve like that. So having given you the idea of the pictorial view of our functions, the next thing to do is simply to go straight with our integration. But remember that our integration is going to be different regions because I have 3. So let's see how the integration is going to be. You start from negative 2 to 0, from 0 towards 2, right? It's going to be 2 parts. So I'm going to have my total area to be equal to integral negative 2 to 0 of f of x minus g of x plus integral 0 to 2 of g of x minus f of x dx. When we say why, you realize that for the first section from negative 2 to 0, our f of x was increasing while the g of x was down. But when I come here, my g of x is up and f of x is down. That is why if you don't draw, you make a mistake. Okay, so here let's see. Making our substitution, a is simply going to be negative 2, 0. And the expression is going to be 3x cubed minus 12x. I remember we did that here when you subtracted. Plus integral from 0 to 2. This side is going to give me negative 3x cubed, right? Plus 12x dx. So after doing this, our simple integral. This is application of integration, so we don't really focus on solving the integral, but our aim is to know how to solve the whole area concept. So at this point, it's simple. Here it becomes, you add 1 to it, and you're going to get 3x to the power 4 over 4, right? And this becomes what? Minus 6 x squared, right? It's x squared. Then you take your negative 2 to 0, then plus, and they come here to negative 3x to the power 4 over 4, right? Plus 6x squared, right? From 0 to 2. And this will give us 24 square units. So